Okay, good afternoon, everybody. Hopefully, this is the last time we have to do the recorded one. So, a couple quick announcements. Ideally, we will be doing office hours on Monday. Canvas Quiz 6 is open on Saturday afternoon. This one is a little different. It is due at 5 p.m. on Tuesday. Tuesday is the last day. This week, we have a short week this week, so please make note of this shorter due date. Also, the final exam has been announced. It is 12 p.m. on Wednesday, April 15th in SRC. Please, CFA students, make your bookings now. So last class, we introduced pericyclic reactions and more specifically starting talking about the Diels-Alder reaction. This is where we introduced concepts of what is known as a diene and a dienophile. These are the two components you need for your Diels-Alder reaction. And we started talking about the stereochemistry, what happens as we do this 4+2 cycle addition, and a quick review of molecular orbital theory, but why we get the geometry and the stereochemistry that we discussed. So today we're going to talk through the Diels-Alder reaction in more detail, talking about selectivity and what we call the endo and exo geometry. So these are different stereoisomers that are possible, diastereomers effectively, from the reaction. We're going to talk about kinetic versus thermodynamic control, and then finally the regioselectivity of this reaction, what geometry is possible in unsymmetrical dienes and dienophiles. So, as we introduced last time, the Diels-Alder reaction is a 4+2 cycle addition. Remember, that's referring to the number of pi electrons, so 4 here and 2 here. Those are rearranged to make a 6-membered ring. The reaction is involving effectively these arrows like that to give us 2 new sigma bonds and moving 1 pi bond over, but it's involving the entire pi system. Most importantly, it involves the highest occupied molecular orbital from an electron-rich diene. So typically what we call a normal electron demand Diels-Alder reaction has an electron-rich diene using the highest occupied molecular orbital, and we are then also using the lowest occupied molecular orbital of the dienophile. So this usually has an electron withdrawing group at that position. So, as a quick review question, try to go backwards. These are the products of a Diels-Alder reaction. Draw what you think the starting materials would look like, remembering about the electron demand that we talked about, which ones are electron rich and which are electron poor, but also the geometry of the product. Take just a second, pause the video and try to draw it yourself. So in the first case, what we're looking for here is, if you notice, the product we're just generally going to make, the double bond is a really good signature because that is something where we have slid electrons over to make this double bond. So usually the double bond resides on what used to be the diene. So we can start off and say the diene is probably this fragment over here. Another indicator is that we've got this lone pair electron donating group here, at least with respect to the pi system. So that's probably going to be our diene fragment. So that would be, I'm going to draw the sigma skeleton first. This represents our sigma skeleton, and the diene would have been here and here. Or once we do the cycle addition, the double bond here is going to remain between these two centers. So if I'm numbering those off, that's carbons number 1, 2, 3, and 4, which correspond to 1, 2, 3, and 4. There's no other relative stereochemistry or substitution we need. Now, if that's true, this bond and this bond are my 2 new sigma bonds, which means this is my dienophile. So the dienophile is carbons number 5 and 6. So 5 and 6 across here would have been the double bond. Now there's going to be 2 chlorines on it. Again, the only thing you have to pay attention to is notice the relative geometry here. The 2 chlorines are trans to each other. They're on opposite sides. So they would be probably like this. Now in the second case, it's a little bit more difficult because you notice there are 2 pi bonds left over. So you could imagine either splitting it this way, this is your diene, or split it this way, and this is your diene. Now, just as because what we're trying to do is focus on something where electron donating groups are on the diene, I'm going to opt for this way. That's where we have our methyl groups attached to the diene, which are our electron donating by hyperconjugation. So in that case, this would be carbons 1, 2, 3, and 4. The two new bonds we're forming here and here, and then that makes 5 and 6, the dienophile on that side. Okay, so that would mean my diene actually looks like this: 1, 2, 3, and 4. The dienophile, we're promoting this back, we're adding another double bond to it. Now notice we have a double bond there, so that would mean we're actually a triple bond is what we started in with. That makes this the CN. CN, those are electron withdrawing groups, and that means we're actually taking a double bond, a diene. The dienophile here happens to be an alkyne, and that would give you the product that you see up at the top. So this is a reminder from last time. Because we'd have two pi systems, the diene and the dienophile are both planar, they can be brought together either from the top or bottom to give us these two different enantiomers. So these two geometries here are mirror images of each other, and you notice that as we do this, there's a lot of common things happening with certain groups in placement. Notice that the two groups in the interior of the diene right here end up both being kind of forced downward below the plane when the dienophile comes in from the top face. Likewise, these two groups here, they end up syn to each other on the back. If we come in from the bottom face, we have a similar sort of geometry where, again, the two interior groups here and here are represented like that, the exterior groups out here. So this is just trying to re-highlight that when we press these together, you have two different possible modes of approach, from the top or from the bottom of the diene, and those end up with two different stereoisomers of each other. However, the relative geometry of the groups, depending where they're positioned, they end up having a similar presentation. Really, this top-bottom geometry just gives you two different stereoisomer products, which are usually enantiomers of each other. So there's one more thing to consider, though. If you imagine that we had, let's say, this diene and this dienophile, there's two general directions that these could be brought together. One where the two R groups over here are basically facing outside. If you imagine that the hypothetical ring that we're forming looks like this, these two are facing towards the outside or outside the plane of the ring that we're forming. We call that the exo mode of approach. However, if the two R groups here are pointing towards where the bonds are going to be formed, so it's basically hiding underneath the ring, we call this the endo mode of approach. So this allows us to show those two possible geometries. So basically, top and bottom are still possible here. What we're talking about is the relative geometry of the dienophile, whether it's coming where these two groups are facing outward or facing inward to the ring. There's still two modes of approach that are possible for both of the endo, from the top face endo and the bottom face endo, top face exo, bottom face exo. Remember, top and bottom are enantiomers to each other. Endo and exo will usually result in diastereomers of each group. We'll show you those both approaches looking here. So I'm showing you, imagine coming in from the bottom face, so it's only one of the trajectories. If we had that cis dienophile where there's two groups located here, imagine there are hydrogens at these two positions. That's why we're not designating them. So we have two functional groups at those positions. We're coming in from the bottom. As it does, we're forming those new rings. That forms this kind of boat-like structure, and you can see what we've done here is these two interior groups are now sort of being pushed up above the ring, and the two groups that were on these positions on the dienophile, they're still cis relative to each other. It gives us this geometry. Going from sort of our chair-like geometry into the normal line bond geometry, again, imagine in this position, if I was viewing this from the top, and I look down across these ones, the ones that will be up towards me, the ones with the filled-in wedge, would be my C, D, H, and G. These ones across here are all up towards me, where in behind that one is my A and B. Those are going to be dash to the back. So what we're trying to emphasize here is that if we go in from the bottom, and these two groups are in the exo presentation outside the ring, what you end up with is they end up being syn to whatever happened to be on these two interior positions. So whatever group used to be at this interior position ends up syn to groups that were in that exo position. The relative geometry across here is what we're setting by having these both be syn to each other. If we do the opposite geometry, so we're still coming in from the bottom now, but notice what we've done is we've taken those two groups and we've tucked them in under the ring. You can see it closer here. When we start to form those bonds, these ones are kind of hiding in underneath the actual ring geometry itself. So once again, it pushes together. Just like we said before, these two interior ones end up sort of puckered up. And again, once again, if I'm viewing it from the top plane, this is my eye, let's say, of sight. If I'm looking from the top, these two are going to be wedged towards me. But now since these two are tucked underneath, they end up pointing away from that position. They end up being anti to those two interior positions. They're now syn to the ones that were in these outside positions here. So whatever was in this group over here ends up syn to that group over here. Again, the relative geometry, whether or not A and E are syn or anti, that's due to endo or exo. If it is wedge or dash at those specific positions, that's the difference between being bottom and top. If I was to actually take this exact same approach, the same endo approach, but come in from the top, I would have the same relative geometry you see here, except each center would be flipped. This would be wedge, 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 and in that case, these two would become dash. So it would be the enantiomer of what you see drawn over here. So top and bottom produces two different enantiomers. Endo produces one where those groups are now syn to these exterior. Exo, these groups are syn to the ones that were on the interior prior. So those are two different diastereomers relative to each other. So overall, if I now put all the groups present, so imagine that, let's say it was tetrasubstituted. I'm just presenting it here so you can see, based on the color coordination, where the relative groups end up. Coming in from the bottom, the two interior groups shown here will always end up, from the bottom approach, those interior groups will always end up in these two positions over here, both syn to each other and both as a wedge when viewed from the top. The two ones here that are on the endo face, you notice that's where they show up over here. They're syn to those exterior groups and obviously anti relative to whatever's attached to them over here. The exo position over here ends up in these positions, syn to those two interior groups that we designated before. So this is a generic template for any transition or any sort of reaction. If you can start off and lay it out where you can see, as seen here, this is why we're giving you just general names. Doesn't matter if they're hydrogen or any group. If you can populate what group shows up at which position around this ring, and you're saying that is coming in from this bottom approach, this is the geometry you'll see. What we're saying is that if the groups happen to adopt the positions here at F and E, that's equivalent to the endo approach, and we'll have that geometry. If the groups happen to adopt this G, H, they would be in these two positions when they're finished at that problem over here. So this gives you a general template for any Diels-Alder stereochemistry. I invite you to just go through this, try to sit with this and use this, because this was very helpful, at least when I was trying to first learn this point. So I'm giving you an overall general template for what this looks like over here and what the diene and dienophile would look like. If you approach from the bottom, you will end up with this geometry where I'm mapping everything out. This doesn't matter about endo-exo because we're saying these two groups are by default going inside the ring. These two groups are going outside the ring. So basically, I'm saying these will always be my exo groups. These are always my endo groups. And I'm just approaching from the bottom to give me this geometry. From the top, it's very much the same. If you look at these two, every stereocenter is inverted. So in other words, top to bottom, they are mirror images to each other. Just coming in from the top, you get the same relative presentation, different absolute stereochemistry at every center. Everything gets flipped. So this template should help you to predict the geometry of any product. And we'll go through one practice example here to just show you what I mean. One more thing I want to show just to help you out too. If you're just trying to look at the relative things, which ones end up on the same face relative to each other, these two interior groups and these two exo groups end up being all syn relative to each other. Likewise, these outside groups and these two groups end up being syn relative to each other. And from the bottom, the red ones are going to be dash, blue ones are going to be wedge. If we do it from the top, same relative geometry. Once again, you can see that the red groups here are all syn relative to each other, and the blue groups also syn relative to each other. It's just that now from the top, the red groups end up being wedge, and the blue groups end up being dash. So these two sort of general ones are just meant to be mnemonics to help you predict what geometry of product you're going to get by properly setting up your starting materials first. Okay, so let's try to use this geometry for this. Now, if you imagine, let's predict all of the possible stereoisomers that could be produced, and that means we've got top, bottom, so we have two modes of approach, and we also have possibly endo, exo for each of those possible. From the top, we could have endo, exo, and from the bottom, we could have endo, exo. Now, in some molecules, because of symmetry, these number of unique possibilities does reduce. And you'll see in this case here, because we have actually a pretty low symmetry, there's a lot of possible products that we could make. Okay, so let's draw this out. Now, if we're going to do a Diels-Alder reaction, the first thing we need to do is redraw my diene in that cis geometry. Right now, it's in the transoid geometry, and that's not the geometry that we're looking for. So I'm going to redraw this now as double bonds like this. And if you note, if I was going to rotate this bond over here, right now, my R prime group would look like this, and the other one will be pointing out. R group like this. So going back to here, I'm just going to copy this picture real quick because this template is going to be useful. Let's keep this up here for reference just for now. Okay, so all I've done is just rotate this bond. That's going to give me a geometry of my diene where one of my R groups is facing out and the H prime group is facing in. Now, just to complete the substitution, that means there's still going to be a hydrogen here and a hydrogen here. Now, looking back at the template that I have up here in this corner, what I want to do quickly is just see which groups I'm populating, or what goes where, basically, as far as how I'm actually designating my groups. This R group here is actually in the position of that A. My C is a hydrogen, so I'm just going to leave that out, don't need it. And this R prime is actually in this position of this D, where right there, that's my B group. And there's nothing back here and here, that's my I and J. So that's what I'm saying is, according to my template, I'm really only using this A position and this D position right now. Okay, now let's line up the dienophile. Dienophile is my methyl, methyl. So that's one way I could possibly draw it. But notice in this one here, I could bring this methyl group together like this. I could also draw it like this. I could also, so those are the two possible geometries I could bring in, right? I can pancake flip these two in these two geometries over here. So what that really corresponds to is the bottom methyl being here and the top methyl being here. That's one geometry. Or I could look at this methyl being in position E and this methyl, at least the blue, this methyl here in position G, right? So those are the two possible different geometries I could have for my dienophile. It could either come in like this and like this. That if basically it corresponds, you can think of it as endo for this methyl or endo for that methyl. That's these two possible points here, right? So I've got two different geometries. And then I've also got, I could bring these together from either the top or the bottom. And then this one as well, I've got top and bottom as well. Now, because of that, there's going to be a possibility of 4 possible geometries that we can bring these components together. So you're going to end up with quite a few different possible products. So what we'll do for now that I've got this one populated in, I'm going to hold it into the geometry that I've shown you up there. For now, I'm going to take this one off. Let's consider just this first geometry here, and let's just do the top approach first. Now, once again, I'm going to go back to that structure I showed you before. I'm going to grab this one here because this is from the top. Copy it, boop, boop. And I'm just going to put this down here. We're going to shrink it down a little bit so we've got it nearby over there. Okay. So we're going to go approach from the top. That's what we have this template here. I've shown you what should end up where. Now we're going to do a Diels-Alder product. So the first thing I'm going to do is draw out my product, which will just be a cyclohexene ring like this. And what I'm going to do with this template is add groups where they're appropriate based on where I've got on my starting material. Now from here, this is my dienophile, or my diene, excuse me. My diene only has something in group A and group D. So from the top, group A will be up. So I have a R group right there. That's where this group was over here. And then down here, my R prime group right there was in position D. Going to our template, D will be down here. This is my R prime. And now we go over to the other side. If you go to look at how we did this addition, in this specific geometry I have here, that's where my methyl group is right here, and my other methyl group is right there. So coming in from the top, my F group will be, F right here corresponds to the first methyl group, so that's going to be on this carbon, and it's also going to be wedge, so that's 1 methyl. And then the H group is the other methyl group right here. It's going to be dash. Now I just want to point out a couple things just as a sort of a gut check. Notice over here, these 2 methyls are anti to each other, so when you're done over here, they should also be anti to each other. This R group is pointing away, this one's interior, these are anti, and once again across the ring, they're also anti to each other. So that relative geometry between what these are or what these 2 are is set by the geometry of my starting material. That's fixed. There's never going to be a possibility where this R and this R prime are ever going to be cis because they're not according to the starting material. Once again, these 2 methyls are anti, so these methyls will always be anti to each other. The only thing that changes based on sort of the pancake flip is going to be the geometry across the bonds we just formed. There can be a geometry where that methyl and this R are syn, or this methyl and this R are anti, as you see right here. The last one too is that this is from the top. If we go and do the same thing from the bottom, the absolute geometry, wedge and dash, will change for everything. So again, this is the first geometry, starting from what you see here, approaching from the top, using that template. Let's go back and grab the one from the bottom. That's this one here. And we'll do that same part. Let me paste it in. And we'll shrink it down just for reference. So if we go this way to the bottom, bringing it in from the bottom geometry, we do the same thing we did before. We draw out our cyclohexene. Now we have our A geometry, that's our R, and you notice now coming from the bottom, it's going to be a dash. The R prime was in the D group over here. It's now going to be a wedge. And since coming in from the bottom again, this was our F group. F is over here. It's going to be a dash methyl. And the last one is our H group. This is going to be a wedge methyl. So notice here, all I've done is the same geometry here, the same geometry here from either the top or the bottom, and look at the 2 possible products. Once again, these 2 are anti as they are here. These 2 are anti as they are here. The only difference between the top and bottom approach is that the absolute stereochemistry across each center has flipped. Well, this was a wedge, it's now a dash, dash is now wedge, wedge is now dash, dash is now wedge. That's the consequence of going top and bottom, is you end up with a complete inversion of all the stereocenters you see, not any relative changes. So we're going to do one more thing. Let's imagine drawing out the last two, where, again, let's say our starting material, the diene, was R and R prime, and our, instead of before, we showed you what it would look like if I was in this geometry with this bottom methyl is endo relative to that R prime group. So what if we drew it in do a pancake flip? Let's say put a methyl down here and a methyl up here. In that case, this methyl is endo relative to this R rather than the other way around that we had it before. Okay, so in this geometry, we're once again going to have top and bottom. Actually, we'll do it the same way. So bottom down here and top up here. So I'm going to go back and we're going to grab these again. How do I copy it? All right, this is from the top geometry. And we're going to copy this one and paste it down here as well. So we've got top and bottom, just as our template points. And I'm going to grab, oh, nope, undo that. I'm going to copy this, and we'll bring it over here. Oops, no, it's not it. Copy, paste. Sorry, 1 second. Cut. Paste. Yeah, there we go. Good enough. All right, there's our templates. Okay, so going through this again, here, the way this is laid out, the only thing I've done now is since I've swapped this geometry, we're only changing some positions. We haven't changed anything over here. This is still in my A position. D is still this position over here. The only thing is, look over here. This first methyl is now in position E. This methyl is in position G. So that's the only change that really we've affected. So coming in from the top, that's that one up of here. We'll end up with our cyclohexene. Once again, dash is R. Wedge down here is my R prime. Notice again, these are anti to each other because they're anti over here relative to each other. The methyl in my E position is dash methyl, and in G is wedge methyl. So notice these are anti to each other. These are anti to each other, but because I've come in from this other alternate geometry, these two are now cis, whereas before these two were trans. That's the difference of sort of the relative positioning. Bringing this methyl in, effectively endo to this group, ends up with them being cis to each other over here. Now doing the same thing from the bottom, that's just this template over here. We are going to, we're still populated the A group. So once again, oops, that's the same one. Poop. Sorry, that's the correct one. I actually just drew the bottom one, so let me just redraw that. This is actually the bottom geometry. What I did accidentally is I copied the same template twice. This one up here is actually from the bottom. We'll go back over here and grab the one from the top. Copy. There we go. That's the one there. So A is my R group. R prime is my D group. R prime. my E group right here will be wedge also, methyl, and last one, G back here is dash. It's my second methyl group. So once again, if you look at these two, these are now syn, these are now syn, which is different than the previous two. That same reflecting happening here. These two are anti as they are there. And once again, top and bottom, every dash is now a wedge, dash is now wedge, wedge is now dash, wedge is now dash. So I encourage you to go back, practice using the templates and laying things out. That's very helpful for sort of helping to do these kinds of problems for your geometries. Now, I want to make a quick note about the endo versus the exo approach. In general, endo ends up having a slightly lower kinetic barrier, means it forms faster, even though you generally form a product where the groups are sterically encumbered. So your final product, based on the geometry, is actually less stable than if you would approach with that same group outside the ring in the exo geometry. However, the transition state to form it is actually a little bit higher. So what you get here is the kinetic product generally will give you this endo geometry. However, if you can allow it to equilibrate, basically if this can then go back to starting material and come over, you end up with the exo product thermodynamically being favored. Now, why is endo favored? Now, and again, endo is really only favored with a specific kind of diene. If our dienophyte has a pi system, or pi conjugated system, such as this group over here. So in this case, the dienophyte I would have in this example, let me just draw this out. The diene here would simply be this. The dienophyte that I'm showing over here would actually be methyl and aldehyde, like this. So here's a case where the dienophyte has this pi system attached to it, and as a result of that, having that pi system coming in underneath this ring, closer to this newly forming point, actually is what we call secondary orbital overlap. Remember, up here in this part here, we have our p orbitals. Those p orbitals will tend to overlap with the pi system in the dienophyte, and as a result of that attractive interaction helps to lower the barrier, making the transition state to the cycloaddition slightly lower. So while in general endo addition is slightly lower in energy, it's kinetically favored, if your dienophyte has a pi system, a pi conjugated system in it, such as having a carbonyl of some other kind, then that really, really helps it out. It helps to stabilize the transition state, and that gives you selectively the endo approach. So while you may run the Diels-Alder reaction, you may get multiple products. Running a Diels-Alder reaction where your dienophyte has a pi system will very strongly favor the endo product kinetically. So let's look at this example. Here we have a nice symmetric molecule. This is something where we've got only the substitution on one ring, and we've got clearly a pi system here and here. So that's an example where that pi system is going to strongly help to favor the formation of an endo approach. Now, notice since this is kind of locked over here, the product we're going to be making, I'm just going to sketch it out. We're going to be making something that is going to look, again, like this. This is the product we're trying to geometry we're trying to make. These are the two new bonds we're trying to form. It just so happens in this case that there's already a bridge between these ones. So if I number this out, that's carbons number 1, 2, 3, and 4, and then carbons number 5 and 6. And what I'm trying to draw over here, this would be carbon 1, 2, 3, 4, and 5 and 6. That means carbons 1 and 4 are also tied together by way of some bridge like this. So in the flat plane, it's going to look something like this, where there's kind of a bridge over the top. So this gets a little bit hard to draw in 2D. So what I'm going to do is draw it in the sort of Norbornene-like cycle. That means what I'm actually going to draw this as is this. This is kind of the geometries we were showing before. Double bond across the back. where I'm going to say carbons 1, 2, 3, and 4 are here, and carbons 5 and 6 are here and here. Now in this geometry, it's a little easier to show that there's a bridging bicycle over the top like this. So it's kind of capped off like a house almost, or we can draw this a little bit to the other side, sort of like that. So it's a 2-2-2 bicycle ring. Now in this geometry, we've got our incoming ones. There's hydrogens out here and here. Those are going to actually end up sticking out, and then underneath, bent under the ring, will be our ethyl groups. That corresponds to the Endo mode of approach. So in this geometry, these two groups are sort of tucked underneath the ring, closest to that sort of double bond. That's that secondary pi overlap. So the way it would look like in 2 dimensions, I would also draw this as this is to the down, and we would have our O-ethyl, O-ethyl. Now you could use the template that we laid out before to get the same kind of approach. What I'm trying to show there is that this will be up, these guys will be down, and we'll have the other enantiomer possible too, where we could draw this where everything is mirror image to each other. So with that practice, try drawing this one as well. Try to give this a shot about what you think the product might actually be here. And we're drawing both the endo and exo approach that might be possible from this one. So give both geometries. So once again, let's number these off. 1, 2, 3, and 4. This is going to be 5 and 6. And I'm going to draw that in that sort of house type geometry again, just because we do have this bicycle where we have sort of a cap off the 2 and a double bond back here. So that corresponds to 1, 2, 3, 4. These are my 2 new sigma bonds, and this is 5 and 6. So that's kind of the structure that I'm forming across this. Now, if I do this, there's 2 possible geometries we could make. We're going to have 2 different functional groups here and here. Those are the 2 sort of parts. If this was endo, I would have the CN and H, and then down here CN. Here, let me just redraw that center. So we've got 2 down and then 2 up, like that. Hydrogen, hydrogen, CN, CN. This would be our endo approach. And what I'm doing there is that these 2 are underneath the ring. The exo geometry would be similar, kind of looks like a house with our cap across the top. We have our 2 here and our 2 there. This would be CN, CN, H, and H. This is my exo geometry. If you wanted to draw those in line bond, that would correspond to this one here corresponds to looking down from the top. I would have this up, up. So both of these would be, let's say, wedge like this, and dash, CN, dash, CN. And in the exo, we draw our ring like this. Once again, wedge and wedge. That, and then it is wedge, CN, CN, like that. That would be our exo. Now, for this question, since we don't have any asymmetric center, it looks like there could be possibly a whole bunch of different geometries, but let's take this one by one. You've got 1, 2, 3, 4 centers, and 5 and 6. And notice this is a case where the dienophile actually has a triple bond into it. That's going to help us out a little bit later with the number of possible geometries that we're making. So we start off by drawing our template. We've got a cyclohexene that we're making. Across carbons 2 and 3, we have our double bond. Our new singles are over here and here, and then carbons 5 and 6 are here and here. Now notice, since we started with a triple, carbon 5 and 6 is actually going to still have a double bond left. We're only reducing the bond order by 1 because we're using one of those pi electrons to make our sigma bond over there. Now as a result of that, these are actually still sp2 centers, which means they're still planar across that. We don't have problems of sort of wedge and dash across those two centers. Also, these centers are not substituted. There's no hydrogens. There's nothing. There are only hydrogens there, so we don't have different geometries of the possible products here. The only thing that's missing is carbon 2 has a methyl group attached to it. So we have a methyl group over here. Last thing we have to add in is just our two CN groups, like this and this. And no matter how you do top, bottom, or any other geometry, this is the only product that you're going to make. And again, that's from two different things. This is symmetric, top and bottom. Since we have a alkyne there, we're going to end up with no stereocenters across here. There's still sp2. And since there's no different substitutions here and here, there's no possible geometries of having this from different pancake flips or different geometries of bringing the two ones together. Every combination only gives us this one product. So the last question we have to talk about is about regiochemistry. So we've gone through and said, all right, if this was my diene, this was my dienophile. Now notice that this is an unsymmetrical dienophile where we have an electron withdrawing group on one end and not the other. Likewise, we have electron donating group on one end and not the other. And as a result of that, what we're going to get is not just top and bottom, endo and exo. We now have two possible regioisomers. So top and bottom, those are enantiomers. Endo, exo, those are the possible diastereomers. Here, these are our regioisomers. What I mean by that is notice one geometry here places these two groups in a 1-3 relationship, or here they're in a 1-2 relationship, even though they're still both syn relative to each other. And so these are completely different regioisomers, not just stereoisomers. So what do you think? If we had to try and do this, would you get one, the purple one, or the blue one? Which one is more likely? And here what we're assuming is that because there is a pi system here, endo approach is going to be favored. So we're assuming only the endo approach is going to be happening. That's where this is sort of tucked underneath the ring. So as a result in that, we actually only get one of these particular geometries as a major component. And that we can actually predict this out. So if I was to take this and say, I'm going to draw out the polarization due to resonance. Now up here, if I push down this charge and I actually extend that all the way through, I can draw a resonance isomer of this one that's going to look, sorry, let me draw the sigma skeleton first, OR. Now I'm going to put a double bond here, and a lone pair down there. Now if I add the charges in, that's going to leave an oxygen plus and a minus down over here. So what I'm drawing across this is because of this electron donating character, specifically in the pi system, this overall system has a net charge polarization where it is delta minus down over here and delta plus up at the top. Now if we do the same thing with respect to this one, I'm going to actually pull electron density over here and here. So what that one's going to look like, if I draw its resonance structure, I'll just put it up over here. Oh, so that's going to put a double bond across here. I'm putting a negative charge here and a positive charge over there. So notice what that's really saying is this center here has a delta plus, whereas closer to this end over here, this is a bit more delta minus. So that just means if you look at how we've sort of lined things up like this, in this, if we've got a sort of a net delta negative down over here, and because we're pulling electron density towards it, we also get a net delta negative down over here. There's a coulombic repulsion between these two, the way that it's lined up. In fact, there's a delta plus on this side, which is also getting close to the delta plus that we're sort of showing up over here. So as a fact of that, this substitution pattern is actually going to be disfavored between these two. Again, that same point, it's the same molecule, so remember the net polarization, it's delta plus on this side, delta minus over here. Meanwhile, this is delta plus because of the electron withdrawing character, and then delta up here is more, well, on the oxygen specifically, is delta minus. So as a result of that, you've got this minus plus interaction versus plus minus. The 1-2 substitution pattern will actually win out. So this is a decomposition you're going to have to do for any of these molecules. As you go through it, you're going to have two molecules, identify the resonance patterns, identify where the partial charge is going to be, where it's partial plus and partial minus. And what you're looking for is cases like this, where the delta plus and delta minus can co-locate. That's going to drive the geometry of how these two things come together, the regiochemistry. So let's apply it in this case over here. If we have the same one, let me just draw this one out on the side. We can draw the, again, the donating groups. So if this one here was to push down and out, that's one geometry. So we get a delta minus, delta plus over here. So our oxygen, sorry, let me just draw this out this way, O-methyl, and as I mentioned, this will be my delta plus center, this is delta minus. That's the best sort of conjugation that's going to be possible. Yes, you do have a resonance structure across here, but remember you're going to have both possible geometries where a plus and minus can be shared between both. This is really the only ionizing center that gives you sort of a charge differentiation. Now if we do the same thing over here, this is going to draw charge up, leaving you a delta plus down here and delta minus up at the top. As a result of that, you can see already that if I pair these two together, so let me draw this in, first of all, the geometry that's drawn out like this. That's going to have a delta minus, and down here, delta plus, where we do not have a nice overlap between here. The negative charges, these are bumping up against each other. And in this geometry, assuming we did an endo approach, this specific orientation would give me a product that looks like this, O-methyl, and I'm going to say that goes endo to give me a carbonyl. And generally, this will be disfavored. And again, that's because of this particular overlap. It means if we were to flip this over in the other geometry, so I'm going to redraw this one here in this position. Once again, delta plus over here, delta minus. That's set up better. That's going to give me my other geometry where my carbonyl, let's do dash carbonyl is down here, and my O Me is up here. This one's going to be my favorite geometry just because of how the polarization lines up to give me my charge balance. Okay, thanks guys.